This video will demonstrate how to view the slab design results in ConcreteBending. We will look at the results for two-way punching shear, one-way beam shear, and flexure. Let's get started. In this example, we have an L-shaped slab that is supported by beams running in the y direction along 3 column lines. Therefore, the slab is primarily acting one way, spanning in the x direction. The slab is loaded with both a uniform load and a single circular point load. Looking at the analysis results, we see that bending occurs mainly in the x direction with a positive moment towards the center of the larger span and negative moment occurring in the slab over the beam support. Two separate boundaries were used to create the L-shaped concrete slab in the model. Slab S1 with the smaller area and slab S2 with the larger area. Selecting both S1 and S2, we see that the thickness was set at 7 inches and we have chosen a single matte bar configuration with the top bars running in the y direction and the bottom clear cover was set at 2.5 inches. The optimized design approach was used for both slabs and we have set 3 rebar patterns for ConcreteBending to choose from. Number 4 bars, number 5 bars, and number 6 bars, all at 12 inches on center. Clicking on Design Results, we can look under Modify in the Project Manager and make sure that we are using the correct design specification and that the correct steel strength is being used for the slabs. Also, in the Minimum Steel section, we can specify how we want ConcreteBending to address the minimum steel ratio and the minimum steel placement. Looking over in the project status, we see that the analysis and design is complete, but there is a warning that at least one of our unity checks has failed. For the plate checks, we pass in punching shear, but we fail for slab flexure and slab shear. Also, we have plate design errors. Clicking on Design Filter in the Project Manager, we see that the design information is set to shear unity. Notice that there is a hole in the slab where the point load was located, indicating that the slab is being checked for two-way punching shear in this location. Switching back to the model view, we can see the circular point load and the corresponding punching shear perimeter. By clicking on punching shear under the plate checks in the project status, ConcreteBending generates a report which is set to show only the extreme rows. This means that we are looking at the case with the maximum and minimum unity values, which are highlighted in red and blue respectively. In this table, we see the lengths of the punching shear perimeter, the depth of the reinforcement, the punching shear capacity, the load, and the unity value, which is the load divided by the capacity. Having looked at two-way punching shear, let's go back to the design results and look at one-way beam shear. Looking at the model, we see that some of the plates are red, which indicates that they are failing for one-way beam shear. Turning on flyby information, we can hover over the red plates and investigate the shear unity value. Along the top edge, we are getting values just above 1.1, and at the bottom edge, we are getting one plate with a value of about 1.53. If we go back to our analysis results, we can simply hold down on the right mouse button and drag a line across the slab to get a graph of shear Vx along the slab. Looking at the graph, we see that shear forces spike at the edge of the slab, but are much lower on average. When designing a slab by hand, it is common to average the shear along the section and use that value for design. As designers, we need to make a judgment call on whether or not we think the slab is adequate, even though we have a few plate elements that are failing. Clicking on slab shear under the plate checks in the project status, we generate a report showing the extreme values for one-way shear, and again, our maximum unity check shows up as 1.53. Having checked the slab for two-way punching shear and one-way beam shear, let's move on to checking the flexure demands on the reinforcement. Switching back to design results and selecting the design filter, we can change the design information from shear unity to steel required. Right now, we are looking at a single layer of steel in the x direction. ConcreteBending displays the area of steel required in square inches per lineal foot in the x direction for each plate element. We see the maximum and minimum calculated steel areas that show up in the legend. Also, since the flyby information is still turned on, we can hover over the plate element and see the specific steel required for that element. As expected, large amounts of flexural reinforcement are required in regions where we have large positive and negative bending moments. Switching the direction from X to Y, we see that the steel required in the Y direction is the same throughout both slabs. Since there is little bending in the Y direction, minimum steel reinforcement governs. Note that if the slab had 2 layers of reinforcement, we would have the option to select which layer of reinforcement we wanted to view in addition to the direction of the reinforcement. In addition to viewing the steel required, we can look at the steel suggested in the X and Y directions. Let's go back to the X direction. Since we are using the optimized design approach, ConcreteBending suggests which rebar patterns should be used for each plate out of the 3 options that we gave the slab. The gray element indicates that there is nothing available for design. With the flyby information still turned on, we can see that the max unity is greater than 1 for MS flexure, indicating that the reinforcing patterns we gave the program are not adequate. Clicking on text reports, we can add the flexure design report for the rebar in the X direction by simply dragging and dropping. Then we can click on the unity check header to sort them from maximum to minimum. Our worst case unity check is 1.32 for flexure in the X direction. We can find out a lot of information about this plate in the details column. It says, quote, all indicated rebar patterns fail, and it shows that number 6 bars at 12 inches on center was the pattern that was closest to passing. Also, it displays that our required steel area is 0.61 square inches per linear foot. To get our slab to pass for flexure, we need to increase the area of steel in the X direction. To do this, we go back to the model, and selecting both slabs, we can add another rebar pattern. We will use number 7 bars at 12 inches on center. Now, switching back to the design view, we see that there are no regions where nothing is available, and the project status shows that the slab flexure steel now passes, and also we have no plate design errors. Right now, we are viewing the steel suggested for each individual plate element. We can change the pattern boundary from by plates to by slabs and see which single rebar pattern is needed in the X direction in each slab to withstand the flexural demands. We are also given the option to pattern the boundary by column lines. Since we had a column line at the location of the point load, 2 different rebar patterns are suggested for slab S2. Thank you for watching and have a great day.